Good morning and welcome to our 2 days webinar with the topic Manufacturing Solution for Planetary Gears, High-Speed Hobbing of Small Gear Wheels. My name is Heiko Meyer and I welcome you to this webinar today. With me in the studio is today Jörg Lohmann. Jörg Lohmann is at the EMAG Köpfer, Head of Technology and Product Management. He can look back already to more than 20 years experience in the gear cutting industry, and he would to give us heute some interesting presentation about the efficiency in gear machining. Like usual, you have the chance to ask us directly during the webinar your questions. For this, please use the chat function. Jörg and myself try to answer the question during the session for you. And that's up to now from my side. So Jörg, please.
So, thank you very much for this introduction, Heiko. First of all, thank you for joining us today. A warm welcome on my behalf and on behalf of EMAG Köpfer. So the first thing to do this morning was, of course, to take a look at the list of attendees who have signed in for today's webinar. And I was very pleased to see that there is so much interest among our customers because the list is quite long. So already now, thank you very much for joining. The topic of today's presentation is efficiency in gear machining. The technology must fit with the right machining strategy to an efficient gear hobbing process. Before we start straight through with our topic, I would like to motivate the topic once again in order to give you a little bit a better overview about what it's all about. We are well known as a manufacturer of gear hobbing and worm milling machines, and we offer to our customer efficient hobbing processes. And many times our customers have been asking, how do you actually do this when it comes to develop such a process? And there were a couple of general questions. Which factors do have an impact on the efficiency of a hobbing process? How can we make benefit of those factors and influence them actively, if not progressively? And how does a viable way look like in order to develop an efficient gear hobbing process? So actually the goal of this presentation is to give you a deep look into such a process development process. And now we start right through. We are going to do this by means of a specific case study, a planetary gear. This may be a planetary gear for an industrial gearbox, such as a planetary gearbox, or a helical gear for a fractional horsepower gearbox, but it may also be a planetary gear for an automotive application, such as a transmission of passenger cars. We are going to develop this process now in 6 steps. So first of all, we are going to clarify the quality requirements with focus on the hobbing process. Then we define whether we go for wet or dry machining. We determine whether we are going to use shank type or bore type hobs. We define the kind of substrate, that means cutting material and coating, that we are going to apply. And then we determine the macro geometry of the tool, such as hob diameter, number of starts, number of gashes, etc. And afterwards, as a final step, we will define the cutting speeds and feeds. So in our case study, we have this planetary gear here. It is from a transmission of a passenger car, and we see here the gear data. This is how the workpiece looks like. This will accompany us now during the next 45 minutes when we develop this process. It's module 1375, 31 teeth, 15-degree pressure angle, typical for automotive. OD, outside diameter, tip diameter, is approximately 50 millimeters. It has a helix angle of 20-degree left hand, and the gear length to be cut is 20 millimeters. So we have a couple of basic data that we take a look on now. So the workpiece drawing, the gear data, we spoke about it already. Important is also the material of the workpiece and its machinability, and of course also the material properties at the end of the process chain. That means the material properties of the final product. The surface finish on the gear flanks plays an important role as well. The RA and RZ values, that means the roughness on the flanks, and it may also play an important role, the structure of the surface of the gear flanks. Then we have a couple of additional basic conditions, such as the quantity of parts per annum and per batch that we are going to machine, the available machining time, the shift model, whether we have a single shift, double or triple shift model, and when it comes to efficiency, also the cost structure at the place of manufacturing, such as labor cost, etc., plays an important role and has an impact on the efficiency of gear machining. Now, a brief excursion to a steering pinion. Here we see a typical process chain of a steering pinion. We start with turning op 1020, hobbing, here in this case in accuracy class 7 as per DIN. Hardening, we will have a loss in quality because the hardening causes distortions. And afterwards, we recover the gear accuracy by means of a skiving process. An important question is, when it comes to the determination of the process chain, what is actually the task in gear hobbing? Is it roughing or is it soft finishing? Will there be a subsequent machining process? And if yes, what kind of process? And we need to understand this from the beginning on. Let's come back to our planetary gear. Here in this chart you see usual process chains for planetary gears. And it all depends predominantly on the final gear accuracy, the gear accuracy of the final product. We usually have op 1020 turning, first and second side, hobbing. Then there may be optionally a chamfering process in between. In certain cases it is necessary to create a chamfer along the involute tooth shape down to the root in order to protect the edge of the tooth from any hazard. Then we have usually a hardening process, and then follows hard turning of the faces or the shoulders of the gear and grinding or hard turning of the bore in operation 60. And maybe the process chain is finished there, so we will end up in a gear accuracy class 8 or 9. Or alternatively, there may also be a subsequent hard fine machining process, such as gear grinding, operation 70, or alternatively gear honing, or maybe even combinations of both in particular cases. And in this case, we will end up with a gear accuracy class 5 to 6.
Yeah, there is one question. What regarding the quality which we have at the finish hobbing? What is possible? What gear quality can you achieve with finish hobbing?
Well, with finish hobbing nowadays, with our machines and with high accuracy hobs, because also their development has made huge steps over the last decade, I would say a DIN class 6 is possible. With, for example, a two-cut strategy, if you have a good machine, proper work holding fixture, a good blank plays also an important role, then we may achieve a DIN 6. Yeah.
Okay, thank you. There is also important, if I can add this, regarding the fixture. EMAG is able to producing in our facility in Heubach own fixtures according completely to the requirement for the best gear cutting process.
Absolutely.
I think it's really important point if you are develop a gear cutting process.
Yeah, absolutely. It's very important to have, of course, the required to correspond to the accuracy that we require for such a process, and due to the reason that we have the production of the work holding fixtures in-house in our plant in Heubach, we of course can influence this too, and that's of course a good basic conditions for us.
Okay,
right.
If it's okay, there is one more question already coming in. That's also an interesting question. Do you have the capability to hob planetary gears in grinding quality or to grinding quality?
Well, that's a good question. Actually, I mentioned earlier that a DIN 6 can be achieved nowadays without big trouble. Yes, this is actually grinding quality, but we should distinguish, because grinding may also mean that we have certain requirements regarding the surface structure and the surface and the roughness, RARZ, on the surface, particularly in the context of e-mobility. This plays more and more an important role. So by the one hand, yes, we can hob them to grinding quality, but we are limited with regard to the surface structure and the roughness.
Okay, then the second part of the question is skiving a process for final machining? So it would be a final process for machining. And also the other question, can be done this on the same machine?
Okay, understood the question. Let me go back in our slides to this to this steering pinion. Here, this steering pinion has been made with a Köpfer 160, so it was exactly the same machine. One time we set up the gear hobbing machine for hobbing, and then after hardening, when the workpieces come back from the hardening process, this may be also an external operation, doesn't it? And then it comes back to the same Köpfer 160, and we use this machine for the skiving process. The workpiece is loaded automatically. We will have our automatic timing sensor. There are various sensors available. This can be an inductive sensor. It can be a capacitive sensor. There are different technologies available. And we detect the previously hobbed and hardened teeth, and the tungsten carbide hob will find the tooth gap by means of this sensor. That means actually by synchronizing the two spindles, the main spindle and the cutter spindle. And then we find the tooth gap, and it looks actually similar to a skiving process. We remove material only on the flanks because this is what determines the accuracy of the workpiece, and we will end up in a higher accuracy on the hardened workpiece. By the way, there are certain workpieces like the steering pinion where it is even necessary to apply skiving because there is no sweep out for a grinding wheel. Here, for example, we have a certain usable length on this steering pinion, and if you would like to apply a grinding wheel of 350 millimeter diameter, there is no way because there is no sweep out available for such a grinding wheel. Okay.
Jörg, thank you very much for answering this detailed question.
Hey, thanks. So let's come back to the process development in our case study. When it comes now to determine the process parameters, we need a clear understanding about the influencing factors. What has an impact on gear accuracy and at the end cost per part? On the left side of the slide, we see the gear data, module, number of teeth, OD, pressure angle, etc. And then also the material specification and its machinability. And at the end, of course, the required quality that we want to achieve in the hobbing process. A second important role plays the hob, the diameter of the hob, the number of starts, the substrate, cutting material, the coating, and the number of gashes. And third big issue is the process itself, whether we do a wet or a dry hobbing, whether we cut with a high or lower cutting speed, the feed rate. Also important, how many parts do we machine per setup? There are flat workpieces, flat gears, of which you may clamp maybe even 2, 3 or even more. And in this case, you can also increase efficiency because you can save approach distance. You will only have one time the approach distance of the hob and one time the over travel at the end of the workpiece package, and you can hob multiple parts in one setup. This plays an important role as well. And of course also whether I do climb or conventional hobbing.
Jörg, if I can step in here shortly, you have written the number of starts is an important topic on the tool or on the hob. Yep. Can you shortly explain to us what are the benefits if you are increasing the number of starts?
Okay. Well, usually the number of starts is increased in order to win performance. That means to increase the performance of the hobbing process. So if you have a single start hob, it may have a certain diameter. If you have a two start hob, usually the diameter becomes bigger. So you have an advantage by the one hand because due to the reason that the two spindles are synchronized by the number of teeth, you will have, if you introduce a second start on the hob, you will have 2 times more RPMs on the main spindle of the workpiece. That means at the end a shorter cycle time, but there's also disadvantages. So if you increase the number of starts, you will increase also the hob diameter. And if we consider that we have a constant hob surface speed, for example, make 250 meter per minute, The RPM level will go down due to the reason that we are using a bigger hob as far as the diameter is concerned. And this at the end is negative as far as cycle time is concerned. So by the one hand we have a positive influence, by the other hand also a negative influence. A second negative influence is that the hobbing stroke becomes longer due to the bigger diameter. At the end we can win time, yes, but it is not a 1:1 ratio.
And then that's also a question, can you give us a roughly estimation how you are faster if you have, for example, a hobbing tool with two starts,
okay,
three
so
starts?
If you want to nail me down with the boots on the floor and you really expect a ballpark figure, I would say, let's say with the introduction of a second start, you may win some 20 to 30% of cycle time. And if you increase to a third start, it may be a 40, maximum 50% reduction of the cycle time in hobbing, but not more. So it's not linear. You cannot say 2 starts 2 times as fast. That's wrong.
So then I remember my story. I have one process, or I have one project there. We have to use a 7-start hob. But I remember there was a big problem with the cycle time too. This was only the reason to do this. It was also not really successful.
Wow, okay, 7 starts. Sporty.
Jörg, also there's a question of, I think you will give there some more feedback later, but anyway, I will ask it because it came directly in. What do the solutions for changing batch sizes look like, and how do you deal with the ramp up production? And how does the production scale up?
Yeah. Okay, I understand where this question comes from. Here today, we are having a case study where we talk about high volume production. But of course, there are many of our customers outside in the world who have small batches. And in this case, efficiency may look completely different from what we discuss here. In this case, it can be I think a benefit can be to have a partner who supplies you with a whole set of work holding fixtures. I make an example. We have job shops that come up with 100 drawings. They send us 100 workpiece drawings and they need hobs for different modules, different number of teeth. They require different work holding fixtures for all the workpiece family. And we as EMAG Köpfer, we are well trained in facing these problems. And what we do, we make setup groups. We try to unify work holding fixtures in order to clamp a whole lot of different workpieces. So to make workpiece families and also to standardize the profiles. This is also something so that you may have one hob module 2 with which you machine different kinds of number of teeth. So we have to change the mindset when it comes to small batch production. But here now in this case study, I would now like to come back to focus on the high volume production. Okay?
Thanks.
Right. So come back to our Planetary gear, our 8 transmission of the passenger car. Now I determine simply we are now going to do pre-hobbing before grinding in gear accuracy class 8. This is sufficient before grinding. The next step is to define whether we do dry or wet hobbing. There are potentials of dry hobbing. One important thing is that we may run the hob with higher speeds in dry hobbing. You see a chart here that I have with me. This is a chart that shows the tensile strength of the steel that we machine. On the x-axis and on the y-axis we have the cutting speed. This is not new. This is from literature. It's from the Academy of Esslingen University from the year 2000. And already there, the researchers have found out that there is a benefit between here, for example, maximum tungsten carbide wet to maximum tungsten carbide dry of approximately 30%. So we can run the hobs faster with dry hobbing. This is a benefit that we can make use of. Another benefit is the reduction of coolant-related devices. So the cost that is connected to these devices, of course. If we do dry machining in comparison to wet machining, we will not have the necessity to have filters for filtering the oil. We will not have an oil mist separator, no centrifuges for cleaning the chips prior to recycling them. When we think about hard fine machining, there will be no explosion explosion flap or any CO2 extinguishing system on the machine. And we can save money on this. This is the second potential for dry hobbing. The third potential, that is also quite interesting, is the so-called reduction of the process chain. What does that mean? That means simply to shorten the process steps. In other words, to avoid washing. Once we have machined the workpiece wet, for example, wet turning, wet hobbing, then usually prior to the hardening, the workpieces go to the washing machine. And if we do complete dry machining in the soft stage, we may go directly to the oven without any washing operation, and this saves money, of course. And besides the washing operation itself, it's of course also the workpiece handling. You do not have to handle the workpieces, no transportation from one department to the other, etc. All this allows to save money. But there are also risks. The risks in dry hobbing is predominantly the superficial defects that we may have. We do not have this in dry hobbing. We observe this only in wet hobbing. We observe this only in dry machining. And how are these defined? The superficial defects are defined as all deviations of the tooth topography that are non-systematic deviations. So there are three different kinds of. We see the pictures here, the scratches on the flanks on the left side. These are simply scratches. It's just an optical interference. They do not really damage or disturb subsequent processes. Worse it is with the material greasing, the picture in the middle. It may happen in dry hobbing that material is greased along the flank, and then we have locally increased allowance for subsequent processes. What does that mean? Very simple. We have an accumulation of material on the flank. We harden the workpiece. Afterwards, we have a higher allowance that we actually want. We grind it off, and then we will, on the final part, not have the depth, the case hardening depth that we originally wanted to achieve. This can be a problem. And one thing that can be even worse, that can even really damage tools, is, for example, the chip welding that we see here. Let's imagine you have a red hot chip that is removed and is shot away by the hob, and it bounces back from any sheet metal within the work area of the machine and falls back onto the gear. The chip will still be red hot and thus weld itself on the tooth flank. And if we have such a chip in this gear flank, imagine what may happen to a subsequent process such as honing. It can really damage a honing ring completely. So this is something that we need to avoid. So this is the risk. There are a couple of basic conditions for successful dry hobbing. One I mentioned already. We need to have a complete process chain until the hardening process that is dry. It doesn't make sense to do wet turning, then wash the parts in order to machine them dry in the hobbing stage. The next thing is the workpiece geometry itself. There are workpieces where we machine in the hobbing process some 50% of the whole workpiece volume. And if we do so, where should the residual heat of the hobbing process go? There will always be a portion of heat that stays inside the workpiece. And if we have machined the majority of the whole body, where should it go?
That's a question now. We know from the grinding process, it could happen grinding burn.
Okay.
How is it here with dry cutting? Have we there something like a hot burn or like a mill burn? I don't know if there is a word, but you know what I mean.
Yeah, I understand perfectly what you mean. This is well known from gear grinding. In case of a lack of coolant, or if you have too much power heat in the process, the flank may burn. And if it burns, you have not achieved the hardening, the hardness that you wanted to have on the flank, and then it is a problem and the workpiece is simply damaged. This may happen also in hobbing, but not really hobbing at the soft stage. It may happen at skiving. You may also do dry skiving on hobbing machines. That's possible. And here we have to be careful with the choice of the cutting speed. It may happen as well there, but not in the soft stage.
Yeah. Thank you for this answering the question. There is one more question. out of the audience, and you answer some points out of this question, but I think it doesn't matter. It's interesting. We have always used cutting oil for gear hobbing. What are the advantages for dry hobbing, and how we assure the quality?
Okay. Well, I think I have already spoken about the benefits of dry hobbing in comparison to wet hobbing. One issue is a good question, how to ensure the quality. Well, first of all, we have to make sure that the majority of heat will be removed by means of the chips. That means we have to make sure that we have an appropriate tool for the dry hobbing process. Very important, because otherwise this thermal effect of removing the heat by means of the chip will not work okay, and then we will have the residual work in the workpiece or on the tool, and this can lead to excessive tool wear. So yeah, we have to make sure that we have the right process setup. This is important. And another thing is the shifting strategy. I will come back to this topic later on. When we do the continuous shifting of the hob, when we do dry hobbing, we should choose a larger shifting step in order to distribute the heat uniform over the whole usable hob length. This is something else that helps us to face the thermal difficulties that we may face. And
I think it's also, we have some minutes before, we have the question regarding the quantity, the batch sizes of the gear production. For this is also important, I think, that the dry cutting process, you told already a little bit, it's nothing for 5 parts, 10 parts, so it needs a process development, or?
Absolutely. This is the third point here in the slide. Coincidentally, the third point says, are the required quantities of parts available? Because it must be possible to do long-term process analysis. You apply certain cutting speeds and feeds, you observe the tool wear. How many parts can I make per resharpening? Then you change the parameters, you try it again, and this is a learning curve. And you must have enough workpieces, volumes, production volume, in order to do this kind of process adjustments. Okay. So here we have 3 statements from the year 2002 from the conference Pre-Machining of Gears from WZL in Aachen, and I find them very good because they are still valid today. It says, the longer the process has been developed, the more use of coolant becomes important. The second is, successful dry machining requires proper definition of speeds and feeds, and wet machining is the more forgiving process compared to dry machining. And this is still valid today, even if it's already 20 years over this conference. By the way, we were talking about the customers that have only small batches. Right in this moment, it's important that when we unify tools, module 2, we cut different numbers of teeth, 10 teeth, 20, 30, 40. In this case, we will not have the ideal conditions for dry hobbing. We make compromises on the tools because it may be necessary when we cut two workpieces with higher number of teeth to have a multiple start hob in order to make sure we have good cutting conditions for dry hobbing.
Okay, thank you.
You're welcome. So in our case, come back to our Planetary gear automotive business, we have the number of workpieces per annum that we can apply dry machining. So the next step will be the definition of either we are going to use a shank type hob or we are going to use a bore type hob. And also there are differences, of course, that we are going to discuss now. Here in the figure number 6, in the upper picture, you can see a hob in bore type execution, and underneath it we see a hob in shank type execution. So what should we use? There are advantages and disadvantages. With the shank type hob, we have less interfaces between the drive of the gear hobbing machine and the tool itself. So generally we may say that we can achieve a higher precision. Another advantage is that production-wise, a shank type hob can be made longer, and this leads to a longer effective shifting length. Why is this the case? It's the case because if we take a look at this bore type hob, here we see a picture of a hob with OD 40mm bore size 16 millimeter. And if you have to hone this bore with a high degree of accuracy with reference to the external basic rack, that is already a very precise tool, you cannot do this until eternity, so length is limited. And we see this here, it's realistic pictures from hobs we have had on our machines already. The maximum length here is approximately 70, make 80 millimeters. Here we have some 200, if not 220 millimeters of length. Disadvantage of these shank type tools, they are way more expensive when it comes to purchase them, and they are less flexible because usually the shank is dedicated to a machine type. So for example, if you have one hob for a Cup 460, you may have difficulties to put this hob on a machine of any other machine tool builder. Now comes a slide that shows what I mean or why the usable shifting length is so important. We see here the basic rack of the hob, and we see the gear that is being cut, and we have an area on the left side and on the right side that we may not use because the hob is like a spiral. It has teeth at the beginning, at the end, that are not completely built. Thus, we cannot use them and stress them. And this is why we have to neglect this part at the beginning and the end. And moreover, we have on one side the pre-profile, pre-generating zone where we do not create profile. And this leads to the remaining effective shifting length here shown by means of this blue arrow. This is really what we may use on the hob. And we are going to shift this hob. That means in the picture on the right side, you can see this. We have an initial position 0. We cut a workpiece on this shifting position. Afterwards, we make a certain shifting step, delta y, to the next shifting position. There we cut the next piece, etc., ongoing this way until the whole hob has been shifted through. And then we may start from the beginning again. And this shows now what I mentioned earlier. In case of dry hobbing, we would tend to select a relatively huge shifting step in order to make sure we have uniform introduction of heat into this tool.
Jörg, there's also regarding a question regarding the quality.
Yeah.
What is the quality class difference in dry and wet hobbing?
Well, actually, there is none. I think there is none. If you do a dry machining or a wet machining, there are different factors that influence quality, such as the accuracy of the tool, whether setup has been made properly. We may not allow any wobbling on the tool, neither on the tool nor on the workpiece. This is important. The blank must be of a certain quality. If we have a poor quality on the blank, we will not have a good result in the hobbing process, that's clear. And the same is valid also for the work holding fixture. Also here requirements must be taken into consideration.
It doesn't matter it's wet or dry. Yep. For each process there are many parameters which are influencing the gear quality. And there is one more question into the comparison of dry and wet. How much more expensive is to design and run a dry process compared to a wet process with coolant?
Okay, well, the design of the process is actually the same. What we do now in this case study it's the same work. There is no difference involved, but the difference is to get the process started. When you do the setup of the machine, you start with the first set of parameters, and then we come to the point where we have to observe how many parts per resharpening have we realized, are we on the right way, what happens if we increase or decrease speeds and feeds. And this is where I see the labor or the effort until you have an efficient machining process. Yeah.
Okay, thank you for answering this question.
Thanks. Yeah. Let's come back to our case study. Here we have a cost comparison between shank type and bore type hob. Earlier I mentioned that the shank type hobs are way more expensive. That is true when it comes to purchase them and also when it comes to do the maintenance of the tools. But we have to consider the effect that I mentioned earlier. We have a longer effective shifting range. And we can see here a cost comparison between a shank type and a bore type hob. So both hobs have 50 millimeter diameter. The usable length of the shank type hop is 180 in this case, only 85 in case of the bore type hop, and this is already quite a long bore type hop, by the way. Effective shifting range 166 versus 71. Purchasing price is 2,500 for the shank type hop, only 1,500 for the bore type hop, so there's a difference of 70%. The resharpening cost is also higher in case of the shank type hop, 200 versus 175. Both hops can be resharpened round about 15 times. So parts per resharpening, however, is way higher with the shank type hop as we have the higher shifting range. Accordingly, we can machine 6,500 parts until we have to resharpen the shank type hop, and only 2,500 until we have to resharpen the bore type hop, and this with the same meter per hop tooth tool life. So at the end, if we break down all the cost for maintenance and purchasing on the parts, this hop gives us nearly 100,000 workpieces, the other one 37,000 workpieces. So if we divide all the cost by the number of workpieces machined, we see that the ratio is round about a reduction of 50%. So we have 6 cents on the shank type hop and 11 cents on the bore type hop. It's impressive how we may reduce the cost for tools.
Yeah, that's really interesting, this comparison. But that's the question: with which hop you did it? What was the material of the hop or the coating of the hop?
Okay, yeah, in this case we have taken into account a tungsten carbide hop. This is what we have at the end really realized. We will see this when we come to the result of this case study, and then we will dip a little bit into this detail.
Yeah, and Jörg, there is also one more really interesting question. I saw also some solutions in the market, but I don't see it getting really successful. Is there a possibility on hobbing machines to do hard finishing with a CBN grinding worm instead of a hobbing cutter to achieve today's desired surface qualities?
Okay, I remember some 20 years ago we have done this already. We have really taken a CBN grinding wheel, put it onto one of our gear hobbing machines, and have ground gears, and the results were considerably good. But we have to consider that a gear hobbing machine is a gear hobbing machine and not a grinder. If we have a grinder, we have different requirements as far as the chip evacuation system is concerned, as far as filtration is concerned, and so forth. So to put a CBN wheel on a hobbing machine is always just a compromise. And we as EMAG group, if we want to do professional grinding, we take one of our EMAG SU grinders and do not make any compromises on this.
Yeah. Jörg, thank you for this. If I can add there something, we have a machine where you can hop and grind, but that's based on a grinding machine. That's the G160 Sky Grind from EMAG SU. And there we have a process where we make the skive hobbing at first. Yeah, we have the heated or the heated or the heat treated gear, and then we make the skive hobbing to reduce really the stock allowance to the minimum. And then we have a really reduced grinding process to reach then the requirements today in the gearboxes for electromobility. It's also a really interesting solution. So there we have a webinar some weeks ago. So if you go to our webpage, you find there the Mediathek. There you see all our other webinars, and there you can get a good impression about this solution. Only from my side, this additional to this point.
Thanks. Let's come back to our planetary gear and our case study. Now we have determined, we have already accomplished 3 tasks. Now the next is the definition of the hop substrate and its coating. And then later we will go on with the hop diameter, number of starts and gashes, and then define the speed and feed. When it comes to the substrate and the coating, I brought a chart from the school book, and it shows the ideal substrate. Maybe you have seen this chart already. It gives you here on the x-axis the toughness and the feed rate. It gives you on the y-axis the wear resistance that is more or less proportional to the cutting speed with which we can apply this kind of substrate, and here would be the ideal cutting material. So we have the HSS coated. In gear hobbing we have predominantly 3 substrates that are of industrial relevance. One is the HSS with coating. It shows its advantage. We can run it at a relatively high feed rate. We have the tungsten carbide coated. We can run this rather on a high cutting speed, but we are limited with the feed. So this is the difference between the two. And then there is a relatively new or young substrate among the two. This is the MC90 or speed core. This is a kind of carbon poor PMHSS steel, and this closes a little bit the gap between the two. And in some cases, this is also of advantage. We have to, when we discuss the different substrates, we should also think about how to do the manufacturing of the tools, and we have to consider that with tungsten carbide, chemical decoating may lead to a tool life reduction if it is not made properly. How do we do the decoating of a hob? Usually the hob is used, it is worn, we have to decoat it, and so we put it into an acid bath, and it stays there for many hours until the hard coating resolves itself and goes away. And this chemical bath may attack the cobalt basis of the material, and this may lead to a reduction in tool life. So over the life of a tungsten carbide hob, this effect may lead to a reduction of tool life. This is something that we have to be aware of and that we have to consider. But for the choice, an individual calculation and consideration is necessary, and we are going to do this afterwards. Again, this chart that I have showed you already earlier from Academy in Esslingen, it shows you here the tensile strength of the material to be cut in both cases, and it shows you also the cutting speed, but it shows you here in the second chart also the maximum tooth thickness. I show you these values simply in order to give you a rough idea about how may we run which substrate.
Jörg, if I can step in here.
Yep.
I remember that especially we have also in the market dry cutting operation where the cutting speed is much more higher as the 240, 300 here, which is showing in the table. I remember there was 600, 700 RPM cutting speed per minute. Can you give us there some more explanation to this topic?
Absolutely, you are perfectly right, Heiko. That's really a good comment, because I have shown you this earlier. It is from 20 years ago. In the meantime, the coating has experienced a huge development. So nowadays these values are not that actual anymore. So nowadays, indeed, we have applications where we run the hops way higher. But it was, this is a little bit our personal know-how that we have from application to application. We have a lot of know-how as far as this is concerned, and we are not just giving it away like that. It was just something to show you, to give you a good starting point. Maybe you personally may add some 20% on the values that you take out of these curves, and then you have a starting point to simply to start.
But important is, Jörg, all our EMAG Köpfer machines are capable and able to run with these higher speeds.
Sure, absolutely. Our gear hobbing machines are all equipped with water-cooled direct drives. We allow, for example, the Köpfer 160 up to 12,000 RPMs on the cutter spindle, water-cooled direct drive also on the workpiece spindle, so there is no doubt about it. We are nowadays able to run and to correspond to the capabilities of modern substrates. That's clear. Yeah. Right. So again, to define which substrate and coating we choose now for our planetary gear is not yet possible, because we will have to define this afterwards by means of a calculation of variance. That means we have to vary different parameters, and we'll then take a look at the result, and we will do this at the end of this presentation or study. The next issue is the definition of the hob dimensions. Here you can see in this slide how the hob actually is built. It is nothing else than a worm. A hob is nothing else than a worm. It has a helix, and it has gashes. So this helix is interrupted by axial gashes, and this creates the cutting edges. And in order to make sure it cuts, we will have a profile grinding discs with which we grind the individual teeth. So it is profile grinding. And the question is now, how do we design our tool? And we will later on apply different macro geometries of hobs and see what will be the impact on our final result. Generally, there are a couple of rules. The maximum lead angle for a hob shouldn't overstep 5 degrees. The bigger the module, the bigger the hob will be due to this angle. And the higher the number of starts, the bigger the hob diameter will be too. And of course, the bigger the diameter, the more gashes we can put onto the hob. Well, the definition of the tool diameter, the gashes, and the number of starts has an impact on the accuracy that we will achieve. We have two systematic deviations. Earlier with dry hobbing we were talking about the non-systematic deviations. Now we come to the systematic deviations. Here in this slide you can see this by means of two pictures, the profile deviation and the feed rate scallop marks. First, let's talk about the profile deviation. When we do gear hobbing, we have a basic rack that has a straight cutting edge, and by means of the kinematics of the process, we create an involute tooth by means of this straight basic rack. And due to the reason that it is an interrupted cut and no grinding, no continuous generating grinding, but an interrupted cut, we will create this by individual cuts. And so it's actually not a real perfect involute, it is a polygon shape. And there we have systematic deviations, and we can influence them by the design of the hob. The second systematic deviation is the feed rate. The feed rate will leave, in function of the diameter of the hob, traces on the lead in axial direction. And we can also determine those. They depend on the feed rate predominantly, but also on the hob diameter. Here is a simulation of our planetary gear. You can see the pictures in the root. This is the root of the tooth, and this is the tip of the tooth. So we are looking now onto the flank. This is the axial direction of the flank, and we see here a feed rate that has been simulated 2.2 millimeters per workpiece revolution with a single startup, and we have a delta Y profile deviation of 0.6 microns, so it's nearly negligible. And in comparison to this, we have exactly the same feed rate, but as a hob with 4 starts, and we have 3.2 microns of deviation. And you can see clearly that there is a huge difference with as far as the topography of the teeth is concerned. And we have done exactly the same with by means of a variation of the feed rate. You can see in the picture number 1 an axial feed rate of 1 millimeter per workpiece revolution, leading to a depth of the feed scallops of 1.8 microns. Then simulation B, 2.2 millimeter per workpiece revolution, 8 microns, and 3.5, 20 microns. And I think it's quite obvious to see that this has a huge impact on the topography. And you can also see by means of the figures that there is an influence that is non-linear. That means 2 times, if I increase the feed rate 2 times, I will have 4 times deeper feed scallop marks. And we will see this also in the chart of the gear. If we put the gear afterwards on the gear inspectioning machine, we will see this in the protocol. On the left side, you can see the profile relevant deviation, and you can also see underneath the lead, the measurement of the lead. And by means of these deviations, we will one by one influence the profile relevant parameters FF alpha and F alpha, and also FF beta and F beta in the lead.
Jörg, if I see this protocol, if I look to the single pitch deviation or single pitch error, there is this fluctuation which I see there, or this swiveling of the graph. Can you explain this?
I think you mean the pitch deviation over there,
yeah,
right?
Yeah.
This one?
Yeah, correct.
Okay, yeah. What we can see easily here is that we have values that are positive and negative. So they switch from positive to negative. And this shows that we have applied a hop with 2 starts. This shows you one by one the deviation of the pitch within the tool. And if it was a single start hop, it wouldn't look like this. You see, we have applied a 2-start hop, but even if there is a small deviation in the pitch, it's no problem at all as concerning if we consider the final accuracy in the gear.
Jörg, if I already interrupt you, I will ask you one more question which came up. That's more for the technical details of the machines, but anyway, interesting. What would be the maximum speed of tool spindle and the work table in high-speed hobbing?
Well, usually, you know, we are a professional machine tool builder, and if necessary, we build the machine around the application, if necessary. That means if one has the requirement to have some 18,000 RPMs, we may realize this due to our know-how in machine tool business. So I think as a standard, our CUP 460 comes with 5,000 RPMs on the hop head with the option to increase to 12,000. And usually this is way enough. You have to imagine what this means concerning the hop surface speed. So there's a lot of reserve involved.
Yeah. Thank you.
You're welcome. Well, okay, let's come back to our case study. We come to the last step, definition of cutting speed and feed. How to define this? There is another chart that I'm going to show you. We have here the cutting speed and feed on the x-axis, and on the y-axis the machining cost. How does it usually look like? We have a certain overhead cost everybody has, every company has. We have the tool cost that increases because the higher feed and speed will be chosen. Accordingly, the tool wear will rise, and the cycle time instead will be reduced because the machine cost will be reduced due to the reason that also the cycle time will be reduced. If we add up all 3 curves, we will have this kind of parabola, and our task in order to determine the cutting speed and feed is to find the minimum of this parabola, and then we find the perfect point as far as the cost is concerned. So when it comes to the feed rate, there's still something else that we have to consider. We were talking about the systematic deviations, the feed scallop marks, but what if this is not a problem? There is still a second issue that can limit the maximum feed rate, and this is the stress that we can addict to the tool. So there is a criteria that we have to take into account. It is an equation, empiric equation from Hofmeister 1970, University at Aachen. You can see this in the slide here. And this equation allows us to calculate the cross section of the 3-flank chip. You can see that one of these 3-flank chips that we have in the hopping process here in the chart below on the right side. And by means of this equation, we can determine this chip thickness. And now I come back to these 2 slides. You remember that on the right side, you have the tensile strength of the material to be cut and the maximum chip thickness. And depending on which material you are cutting and what kind of tool or substrate you are using, there are recommended values. And I would say these values are still valid today, by the way. So you can choose for tungsten carbide, for example, a maximum tooth thickness of 0.15 millimeters. And this is a good indicator for the maximum stress. Right, now we come to the conclusion. Now we have a tabella in which we have made a variation of different parameters. On the left side, we see the hop dimensions. We have made various simulations, hop diameter 32, single start 12 gashes. Then we have successively increased the tool diameter and also the number of starts. And remember what I said earlier, the bigger the hop diameter, the higher the number of gashes can be. And we have made cycle time studies for each individual process setup or tool. We have done this for PM-HSS as a substrate with coating, speed core with coating, and tungsten carbide as well. We have the cycle time. besides the cycle time, we have the machining cost per part, and we have also the tool cost per part. And if we add up these figures, we have the total cost for each individual machining process. And you will see one thing, there is a minimum here for the tungsten carbide tool with coating. With this geometry, diameter 50, 2 starts and 15 gashes, we have the highest efficiency in the gear hobbing process. And we have realized this also. You see here an overview or the developed process at a glance. We see the cutting speed that we really apply. It's 450 meters, feed rate 2.2 millimeters with maximum chip thickness 0.17, and the cycle time is less than 9 seconds. And this is how it looks like on the Curb 460 in reality. I think we need to get this movie started. Right. So we see the 160 on the left side, the work area, on the right side, the automation cell. Here, this is in the area of the automation. We have a so-called servo distributor that takes care of the workpiece handling. The workpieces roll down a chute, they roll down by gravity, and the distributor presents the workpieces to our high-speed gantry loader. The gantry loader is equipped with a double rotary gripper, and this ensures chip-to-chip times less than 3 seconds, as you can see easily by means of this video. And you will see how we machine this workpiece with exactly the hob that we have determined earlier. It's a hob diameter 50, 2 starts, tungsten carbide with Alcrona coating.
Jörg, until the end of the video, there is a question. The electrical vehicle segment is very cost competitive to manufacture the gears for EV segment. Which processes would be the best or the optimal one? Hobbing, skiving, shaving?
Well, there is no generic answer because there are different strategies. There are automotive companies that have a certain strategy. They interact, they always mesh a ground gear with a honed gear. Both gears may have the same level of gear accuracy, but they have a different surface finish. And it's not even the RA or RZ value that determine this. It's simply the superficial structure that they have. And they make these two gears mesh together because they have a very good behavior of the two gears as far as friction is concerned. Tribology is it what they call it. And there every company has its own philosophy. So there's no generic answer possible. It depends really on the application.
Okay, that's thank you for answering this interesting question.
Yep. So at the end, I would like to come back to a slide that we have seen already today. It was about the process chain that we go along. We have now spoken a lot about the hobbing process, and we have developed this process together. Usually now we should also consider the Operation 70 gear grinding, because we as EMAG have also very good machines and solutions for this. And I think I hand over the word to you in order to introduce these beautiful machines to our
first,
attendees.
thank you very much for this really interesting 1 hour in deep explanation to define the correct gear cutting process, gear hobbing process. Thank you for this. And like I mentioned it already, please use the chat function if you have still some questions which we can try to answer in the last minutes of this webinar. And what I would to add is EMAG take over in March 21 of the Italian company Sampotenzili, and under the name of EMAG SU, EMAG is now able also to provide to you generating grinding machines, sweat wheel grinding machines, and as well profile grinding machine for gears. So we're starting with the G160, that's a machine up to gear diameter 160 and module max 3 and workpiece length of 300 millimeter. What is really special here is the quick chip-to-chip time, less than 2 seconds. I think that's the fastest machine in the market. So these machines we are producing in Bologna. There is also, if you have application also for these solutions, please contact us that we can offer you as well these interesting gear grinding machines. The next bigger machines is the G250. Here up to module 5. With this machine you can do gear grinding and thread wheel profile grinding and thread wheel grinding. And we have also one more bigger machines, G400 for up to module 8. So there we have many solutions. And what is also important, EMAG SU can provide you as well gear hobbing machines, which starting where EMAG Köpfer ends with the capability of the machine. So modules 5, 6. So there we have the CLC machines, also really famous Italian machine building technology. So that's also a quite new solution. And we was discussing today about several gear manufacturing processes, and one also really popular process which is in discussion at the moment is power skiving. In German it's called Weltschälen. So if you have there interesting applications, we have every time a machine in Saalach located that's called VSC 400 PS. That's a machine based on our famous VSC series, which we have more than 3,000 types in the market. It's a really rigid machine with mineral cased bed and hydrostatic C-axis in the spindle, and there we did already power skiving solutions up to module 5. And so if you have also interesting things there, please contact your salespeople that we can arrange here a visit to see, that you can see our solutions there. That's from my side. Is there some more questions? I saw there is one last question, I think. Jörg, I think this we can answer. For large production runs, how do you handle hop changes and how fast can it be changed?
Okay, understand. Well, the hop change, if I consider our latest development, the HLC 150H, a horizontal gear hobbing machine, this machine is equipped with quick clamping devices. How does it work? You have one button on the operations panel, you press this button and the counter support will go away automatically. Then you have a foot pedal, and it must be a foot pedal, I explain to you why. And you press this foot pedal and then you can take out the hop from the hop head. You take the already prepared, externally preset hop arbor or shank type hop, put this to the machine, and once again you press the foot pedal, and afterwards you press the button on the ops panel in order to bring the counter support back into position. So it's actually 2 times pressing a button and 2 times activating a foot pedal, and that's all what it needs. So this goes really quick, but I think the question goes in another direction. The problem is usually that once people have changed the hop, they do it quickly, but then afterwards you have to make sure that you are right on the right diameter, and in many cases people are not allowed to run their machines until the workpieces have been measured and they get approval for production. And this is usually where many customers lose way more time than when changing the hop. But that's also just a question of organization. What we can do, we can already measure the hops outside or use tabellas, resharpening tabellas from our hop suppliers, and then it goes quite quick to be back on quote.
Jörg, one more last question.
Sure.
What is the maximum module in high-speed hobbing? That's also, yeah. What is high-speed hobbing? What is the maximum module? Interesting question.
This is now getting a philosophical question, because I think it is not well determined where does high-speed hobbing begin and where does it end. And the same is valid also for the module. I think there are fluent limits. You cannot say starting from module 4 on it will be high-speed hobbing or similar. There is no way. But yeah, for further discussions, please feel free, make contact with us, with your original sales manager. And well, I think we have arrived at the end. Thank you very much for joining us today. It was a pleasure to hold this presentation. And See you soon.
Yeah, Jörg, thank you very much again. It was really interesting. Thank you to you outside which joining our webinar. Please look also to our webpage. There you see the other dates for the webinars. And like Jörg mentioned already, if you have interesting project, please contact our sales team worldwide. Or you see HappyWise, the exhibition season starts again, and you can have the chance in all your markets, have next year shows where EMAG is present, where you can also meet our local sales team or as well the teams for our technology company like EMAG Köpfer, and you discuss deeply with the guys then your questions and topics. So thank you very much again. See you soon. Have a nice day, a nice week. Bye bye.
Thanks. Bye.